in this section, we would like to establish a model to describe the vibration of a string, and then to find the differential equations that which model this vibrating string. So here we have so suppose we have a string, right, located in the segment of the x-axis. Okay, and from 0 to L. Okay, so this is the string. All right, and by deflating the string a little bit, and then we release it at the time 0, then the string will vibrate. Okay, will vibrate. Okay, and so okay, and so we will like to, so for example, at some time, okay, and the U of t and the x. Okay, so this is the diffraction in the y direction at time t and the horizontal position x in 0 and L at time t greater than 0. Okay, so this is the diffraction in the y direction. Okay, we want to know the difference in the y directions. And at the time t, all right, and the horizontal position x here. All right, so now reasonable assumptions are made as follows. First one, the string is homogeneous. Okay, i.e. the mass rho of the string per unit length. So rho is the mass density. For example, the unit will be kilogram divided by meter. Okay, so that is per unit length is constant. Okay, throughout the string. Okay, so that before we deflect the string, that when it sits on the x-axis, okay, we see the string is homogeneous. It means that the mass of the string per unit term is constant. Okay. And we also want that the string is perfectly elastic. Okay, and it does not offer any resistance to bending. Alright, so there is no resistance. Second, okay, here, the tension T caused by stretching the string before I fastening it at the two end. Is so large that the action of the gravitational force, okay, on the string the gravitational force is trying to pull the string down, right? A little, okay, can be neglected. Okay. To have a vibrating string, as we know, we have to stretch the string so that there is the tensions on the string. Okay, before we fasten the string at the two end points 0 and L. Okay. Otherwise, if the string has no tension, then you can't vibrate it, right? Because it will be too loose. Okay, so if you have any experience with any string musical instrument like a violin or guitar, okay, or so some traditional Chinese musical instrument like ohu, something like the string instruments, you see that you have to fasten the string. Okay, otherwise there is no vibration. And so the tension, so you have the tension, and we assume the tension is relatively big enough to the gravitational force. You know, the gravitational force proportional to the mass of the string. Okay, and usually because the mass of the string is so small, so the gravitational force will be small compared with the tension. Okay, so we just neglect the action of the gravitational force. Okay, so the possible force involved into the string vibration would be the tension only. Okay, that is the key point. All right, so we just neglect the gravitational force. And the third assumption is that the string performs a small transverse motion in a vertical plane. Okay, so it will, the string, this is a vertical plane, like our chart, the blackboard here, and so that the string will vibrate in this direction. Okay, and we assume that the diffraction is so small. As you can see, if you look at the vibration of a violin string, the vibration is quite small. Because the tension is actually very big. Okay, so that the vibration is quite small, and so the transverse motion is in the vertical plane. Okay. This is some kind of an ideal assumption, because if a real string vibration that it can move okay, to beyond the vertical plane is possible. Okay. And so that the diffraction and the slope at every point of the string always remain small in absolute value. Okay. Okay. So this is a very so the diffraction. All right. So the diffraction, because that we assume that the string will transverse in the vertical plane. All right. So the diffraction actually measures in the y direction only. Okay. And the diffraction in the slope, okay, that will be small, okay, and absolutely makes it, because the slope can be positive or minus, right, and the diffraction may be in the positive y or minus y, but the absolute value will be small. Okay, so this is the small vibration. All right. Now we take a look at the local property of the string in vibrating mode. So let's so we zoom in, say, some parts of it, this part, okay. And so that we zoom in this part, okay, and so that this is become to and we select, okay, the 2 points. So here this is x equal to, so we have a point, this point is P, the other point is Q, here. So let me describe it. This is just like okay, we just zoom in, okay, the local here, and see, so that so the location here is x, right? And this point is x plus delta x divided by 2, and this is x minus delta x divided by 2. Okay, so we look at the point x between 0 and L, right? And the small element, okay, corresponding to delta x there. Okay. All right, and so here we have P, and we have Q. Okay, right. So we look at so now we have this. Look at here, okay, right, and the corresponding y-axis, this is x plus delta x divided by 2, x minus, and x plus delta x divided by 2 here, okay. Now the tension, okay. Let me pick up another color. Okay, so the tension is here. We call this is T2, T2, okay, and another tension, T1, okay, and the angle here, and also the another angle. So this angle we call beta, okay, and this angle we call alpha. Okay, now, so T1, okay, so T1 has horizontal component and the vertical component. Right, so that the horizontal component will be T2 and the cosine beta. And here, the vertical component is T2 sine beta. Similarly, we have okay, so the horizontal component here is T1 cosine alpha, and the vertical component is T1 sine alpha here. Okay, so you see here, and the alpha and the beta are our assumption that they're corresponding to the slope, right? And so they are all small, they are quite small, okay? Any questions about this local view of the string? Any questions? No? Good. All right, so we have that. So now, So the mass rho of delta x, right? So the mass of a string element in x minus delta x divided by 2, x plus delta x divided by 2. Okay, so the mass. So this math, okay, has no horizontal motion, so that the horizontal components of the tension were balanced or cancel each other. Okay, so as you can see that because that the two horizontal component will be in anti direction, so that we know T1 cosine alpha should be equal to T2 cosine beta. Okay. Okay, so that they have, and we call that this tension is constant. But the vertical diffraction is caused by the net force. Okay. And the net force is F equal to T2 sine beta minus T1 sine alpha. Okay. Okay. So now, and the net force would be by Newton's law. Okay. So this is the acceleration of the point mass in this interval. Okay, so this is the acceleration here. Okay, and this is the mass of this this element, small element there. So this is by Newton's law. Newton's second law of motion. Okay? So we have this is our equation, and we have this equation here. So if we divide both sides, okay, now dividing both sides by t. Okay, so we're dividing both sides by t by this t here. So we have T1 sin beta divided by T is equal to T1 cosine, but cosine, sorry, T2 beta, and the T2 cosine beta minus T1 sin alpha divided by T1 cosine alpha equal to rho delta x divided by T, and the acceleration. Okay, now you can cancel them. So you have tangent beta minus tangent alpha is equal to rho delta x t. Okay, right, good is the question. Now, the tangent here, tangent beta, tangent alpha is actually the slope, right? The slope of the tangent line at the point Q. So this tangent beta, tangent beta at Q, and the tangent alpha is the slope of the tangent line at the point P. Okay. All right. And so now the tangent beta is actually, so now is the positive to be relative to x, right? The x coordinate. When x is equal to x0 plus delta x divided by 2. So maybe I write it. So this is x0. Sorry, x0. Okay. And the tangent beta is the first derivative at x equal to x0 minus x divided by 2. Alright, and then we move delta x to the left-hand side. So we delta x here, and then we have u x0 plus delta x divided by 2 at t. Okay, so this is tangent beta minus tangent alpha, sorry. this is alpha. So this is x0 minus delta x over 2t. Okay, so the difference equal to rho t square. Alright, and by letting delta x go to 0. Now, by letting delta x go to 0, this is actually the second derivative, okay, with respect to x. Okay. And so we have rho t square. Okay, so which is one-dimensional wave equation. And the physical quantity or the physical constant tension divided by rho. And the tension is the force in Newton, right? But what is Newton? 1 Newton is equal to is the kg, right, and times m, and second square. Because this is the mass and this is the unit of acceleration. Okay. And how about the mass density? Mass density is kg divided by m, right? So together, so the unit is equal to m and the second and the square. Okay. So that we let this constant okay, has a dimension is m square second square, and will be denoted as c square. Okay, so it's the square of the velocity. Okay, the c square, and we will see how do we interpret this velocity c. Okay, what the velocity? So we will see. Okay. Of course, it's not the velocity of the vertical diffraction, right? Because the vertical diffraction has velocity which is not constant, right? Because it's vibrating. Okay. So what is the velocity of c? We will see that later on. Okay. All right. So now we arrived at the one-dimensional wave equation. Okay, so this is the partial differential equation which govern. So this equation, governs the diffraction, and diffraction u xt of the vibrating string. Okay? Vibrating string fasten at x equal to 0 in the L. Okay? So that you fasten it alright, at both ends. And the tension here, with tension T, okay, with tension T, and the rho is the homogeneous mass density of the string. Okay. Now, so roll together with the C here. So this is become 2. So that, oh, is that correct? Yes, okay. Yep. So that's usually, so this is saying that T C square. Okay. So this is the standard form. Oh, no, not here. Should be here. Okay. Okay. And this one corresponding to this is the standard way to write down the one-dimensional wave equation. Okay. Okay. So C square is here. All right. So now we want to solution. We want to solve this one-dimensional wave equation. So solution by separating variables. Alright, now, so since the string is fastened, okay, at the two ends, x equal to 0 and x equal to L. So we have two boundary conditions. Okay, so the boundary condition at U0t and so at any time, the vertical diffraction of the string at x equals 0 will be 0 because this is fastened there, right? So that, and then at L and T also 0 for all t greater than or equal to 0. Okay. So this is, we have two boundary conditions here. And furthermore, the ongoing vibrating or vibration, maybe I say, the ongoing vibration of the string well, depends on the initial diffraction. Alright, the initial diffraction means the diffraction at time t equals 0. For example, if you do not do any if you do not pull any of the string, just that the string remain stationary, then there will be no vibration, right? So the U will be 0, UXT will be 0, or OX and OT. Okay? And but if you have defect the string in some way, attempt T0 and release the string, then you will have vibration. And so that the following vibration will depends on the initial the diffraction you have. Okay. So we call it. So the initial we're going to call it f of x. Okay. And then possibly and then maybe on its initial velocity. It means the velocity at t equals to 0, and call it g of x. Alright? So that's, we have two initial conditions. Alright, so we write the initial condition. At time 0, okay, we have initial diffraction. So this is the initial position of each small element of the string. Okay, and the velocity. So velocity will be the first partial derivative with respect to t. Alright, x0 will be g of x for all x in the string here. Okay, and of course, as you can see that, when at x equals 0, because it is always 0, so you can see that. So we can make a remark. Alright, so by the boundary condition, at x equal to 0 and x equal L, so we have So we have 0 equal to u 0, 0 always. Okay. Okay, the boundary condition. It's F0. Okay, and 0 equal to u, L 0. Okay, and this is f of L. Okay, so the initial diffraction f of x should be 0 at both ends. How about the velocity? Because for all t, this is 0. So if you take the partial derivative for t, then the velocity is also 0. Okay? So you can see the 0 is also in ut, 0 and 0. And And this is G of 0. 0 is equal to ET. 0. Yeah. Okay. So the initial diffraction as well as the initial velocity will be 0 at both ends. So this you should have. And now, so now with the two boundary conditions and the two initial conditions, then we will know that there was only one and only one solution in the physical sense. Because that is the vibrating stream. you know that by experiments, right? So there should be one possible solution because you observe the string is really vibrating. Right? Starting from 0. Okay? And the path, this is causal, right? So that this is the dynamics and which follows the mechanics. Right? The following mechanics follow the Newton's law of motions. Right? And so in the physical world, you should have one and only one solution. Right? So the existence and uniqueness is found from the physical, from the physics. I can say that. Even though we didn't prove it mathematically, right? But we believe, right, that this is just a follow from mechanics in physics. So now we know there's one, and then so from physics, from mechanics, classical mechanics, from classical mechanics, there is one and only one solution U of xt, right? Of the one-dimensional wave equation. Okay, the one-dimensional wave equation. Okay, together with the above two boundary conditions. Okay, so let's say this is equation 12.3.1, this is 12.3.2, and now is 12.3.3. So that the two boundary conditions in 12.3.1 and the two initial condition in 12.3.2. Okay. Right. So now we'll proceed to find a solution. So we now proceed to find a solution of the PDE in 12.3.3 and satisfying (12.3.1) and 12.3.2. Okay. Right, and this method is called the separating variable. So they are 3 steps. As follows. Step 1. By the way, the region, okay. So that U, the defining region. So we want to know that X is from 0 to L, and so this is the term, okay, to R. Okay. So the solution, the U, right? The U, and the defined domain will be so that because it has 2 independent variables. For the X variable, the X is in this finite closed interval, and for the time variable is in this semi-infinite ray. Okay, so here, so that U is there. And for these differential equations, we usually, so this is a region, right? So this is a region. Right? So this is a region in the plane whose interior is the domain. The domain, what domain? Okay, so this is the open connected state. Okay, so if you know that, so this is X, this is the defined domain, and it will consisting so this is the domain, right? So it's an open connected, of course, right? It's an open connected subset, right? So this is the domain here, and the region, including the boundaries, all the boundaries of the domain. So you see that because within the 2 endpoints, okay. So the R. And so the R here, including, okay, so this is our region, okay, and this is the domain, D. The domain, D equal to here. Right. So the PD for PD we will specify that for all, because we want that the PD to be, so we satisfy. Alright, so that here. So it's here. Right. And usually we want the solution is continuous, right, on the boundary as we specified, right? We usually want that So the PD is satisfied interior of the region, okay, and we want is continuous, okay? The continuous on whole the region here, okay? So this is the continuity we have, we ask for. All right, so, okay, so let's take a break, okay, up to 2:20, okay? All right, so now we will proceed to find the solution. Okay. So step 1. So by the method of separating variables or so-called product method, we set u of xt equal to f of x and g of t, right? So we try. Basically, this is just a try and error method, right? So we want that to seek for possible solutions such that the solution is the product of two functions with respective variables. Okay, so this is just trying to find, and then right, so this is our trial. So now by substitution u of xt equal to f of x and g of t, right? So that we want the solution to be x in and t. Okay, so we want that. Okay, so into the partial differential equations, 3. So we have, so now for this one, because this is positive with respect to t, so for the left-hand side, we have f of x, and we have the second derivative of g of t. Okay. So now this is become the ordinary. This is not partially positive derivative, just ordinary derivative. And here we have, again, the right-hand side, we do the partial derivative with respect to x only. So we have the g of t and the square of f of x here. Okay? So now we divide both sides, okay, by, right, so by the c square and fx and g of x. So we get c square gt, right, here. So basically we move this to the left-hand side and f of x to the right-hand side. And this is d square and dt square gt equal to 1 of f of x and the second derivative of f of x. Okay. Well, now, so you see, the left-hand side depends only on t. Okay, so this is a function of t. But the right-hand side is a function of x. It's a function of x, right? So this is the power of the variable. Okay, so by this variable, the partial differential equation, you can see that becomes to ordinary differential equation. But and because that we do the separating variable, so the left-hand side depends on t, the right-hand side depends on x. So that means that they should be equal to a constant. Okay, a constant. Because why is a constant? Because it does not depend on x and no t. Okay. All right, and so that so things the left side depends. So left hand side depends only on t, while the right hand side depends only on x. Both sides must be equal to a constant. And we say this constant is k, right? So now we have c squared g of t, d squared dt squared a1 of f of x, d squared f of x, and equal to k. Okay, so this yield two ODEs. So we have that g double prime, okay, minus k c squared g equal to 0, the first equation, and for the second equation we have f double prime minus k and the f of x equals 0. Okay. Right. So by separating variables, our PDEs change to two ODEs. Okay. So we have two ODEs of second order. Okay, here, this is step 1, and step 2. So step two we have we should solving ODEs, okay, with boundary condition. Okay, so let's see. So that they should have boundary conditions, right? And now, so we have to identify boundary conditions for G and for F respectively, right? So now that the boundary conditions in 12.3.1 are here U0t, which is f of 0, and g of t is 0, and then u of lt, which is f of l, and g of t it's 0 for all t greater than or equal to 0. have a typo error. Okay, so we have this one. All right. But if look at here, so F0 is real value, okay, and the G of t is 0. Overall GT is 0. Now, so if GT is 0 for all t greater than or equal to 0, right? So if GT is 0 for all t, okay, then by here, then U of tx, okay, is 0. Okay, for all uxt is 0 for all x in 0L and t equal to 0. Which is trivial. Right? Which is trivial. We always have trivial solution because the one-dimensional wave equation is homogeneous and linear PDE. Okay, so that there's nothing new. Okay, so we will assume, of course, we will assume that G of t is not equal to 0 for some t greater than or equal to 0. Okay? Alright, so at least one of t, such G of t is non-zero. So if this is non-zero, then f0 should be 0, right? And the f of L must be 0. Okay? So then we have, okay, so then we have f0 is equal to 0 and f of L is 0. Okay? It's 0. Alright, so this boundary condition is 12.3.6. Okay? So these two boundary conditions is for this second order ODE here. And with two boundary conditions, we know that they are unique solutions, okay? Because ODE has 2 degrees of freedom. This is a homogeneous linear ODE with constant coefficients. So from our experience in ODE, we know that the general solution has 2 degrees of freedom. And so with two boundary conditions, we can uniquely determine the solution F. Yeah. Yes, please. Where? Which assumption in here? Oh, why we use the separating variables? Yeah, we try to find such kind of solutions. Yeah. Maybe if we assume that we have separating variable, maybe we cannot solve any non-trivial solution. It's possible. Initially, we don't know, right? We don't know. All right? So people trying to simplify the method. So it's kind of greedy algorithm, right? Because we know from case of mechanics, we know there's one and only one solutions. So try to find one. Okay, try to find one solution for that. And okay, so that we try this method. So it's a method, but we apply a method does not guarantee you can find a non-trivial solution. This is no guarantee. But fortunately, for this case, we are able to obtain non-trivial solution, as we will see. Okay. So this is just a greedy idea. Okay, we try by using such a simple method. Yeah. Okay, and so people did that way and got success. So that's why we represent this method here, because it's very simple. Okay, so now we obtain two boundary conditions for this ODE. Okay, for this ODE. All right, and so that so if k equal to 0, then a general solution of the ODE in 2.3.5 is here, is f of x equal to ax plus b. Okay. Okay, so if k equals 0, then this ODE is a general solution, and by applying with the boundary condition in 2.3.6. So we have A equal to B equal to 0. So that f is the 0 function on the L, and then u of xt is 0. Okay? 0. Which is trivial. So when k equals 0, we don't have, because we don't know what is k, right? We just say that there must exist some k, okay, and we have that. So k is still unknown, But when k is 0, then we know there's no solutions, okay? And if k is positive, alright, with mu positive, then a general solution of this ODE is AE mu x plus BE minus mu x for all x in L. And again, by a two boundary condition in the equation 12.3.6, we have A equal to B equals 0, which makes that f is equal to 0. Okay, and this implies u xt is equal to 0. A trivial solution again. Alright, so today I'm not not good enough. Now the third case, if K is it's negative, then a general solution of the ODE in 12.3.3.5 x here, f of x into a cosine px plus b sine px, okay, for x in 0. Okay, and by 12.3.6, okay, first of all, f0 is 0, but f0 give you a, so a must be 0. And 0 is FL. Now FL give you b sine PL. Okay, should be 0, right? So that to have a non-trivial solution, to have a non-trivial solution, we must set b not equal to 0, and then sine PL must be 0. Okay? Sine PL must be 0. So that this is even only if that P is equal to n pi divided by L. Okay, and for n, 3. Okay, so to have, so with separating variable, method, now to have a non-trivial solution, right? Because our goal is to find a non-trivial solution. Okay, so we define f of f sub n of x to be sine n pi x divided by L, okay? Because that P, the only P is n pi divided by L, so n divided by x, okay? For each n, so, okay? So that for each n, f sub n is a solution of the ODE in 12.3.5 and satisfying the two boundary conditions. Okay, so now up to now we are still on the way, because that if k is 0, our k is positive, we go to the dead end, right? Right, so this is already dead end, so we just stop there. But when k is negative, okay, we find that, right? We find that certain k, right? Because this is minus p square, and certain p give us non-trivial solution. So we're still alive, but not at the end, right? Because we should find a solution u. But at this moment, we're still alive because we find f solution, right? So we define that f sub n, which are solutions, of the boundary boundary value problem in 2.3.5 and 2.3.6. So the OD is in here. We put boundary conditions there. So this is a boundary problem, and we find that that is for each n, okay, the corresponding kn x bat is minus n pi l square. Okay. Right? So the k should be k sub n. Okay. For those k that we do, we still have a non-trivial solution. So we're still alive up to now. Now, okay. So we next solve. So we next solve the ODE in 2.3.4 with k equal to kn, which is minus n pi by L square. Right? So we have a gn, g double prime plus, and because we have the kc square, right? Here we have kc square, but k is that number, so now we have minus k and c square g, so 0 is this one, and which is plus n pi c divided by L square g. Okay, and we note that this is the angular frequency plus omega n square g. Okay, where omega n is defined to be the NC divided by L. So you have the angular frequency here. This is the angular frequency there. Okay. And so a general solution is here. We call Gn T. Okay. So that is Bn, and the cosine omega nt plus Cn sine omega nt. Is that okay? So now we obtain a sequence of general solutions of the one-dimensional wave equation in 2.3.3, right? And then this is U n xt. So U xt is Fn x and the Gnt. So this is the Bn cosine omega nt plus Cn sine omega nt times sine n pi divided by L x. Okay, for n 1, 2, 3, etc. Okay. So you see that we have a sequence of general solutions, okay, of the one-dimensional wave equation in here. Okay. Okay, so this is general solutions. Okay. And so the functions use sub n xt with bn cn arbitrary, but not both zero. Right? Because if both of them are zeros, then this is trivial. Right? It's true. So we called eigen functions or characteristic functions okay, or characteristic functions of the vibrating string corresponding to the eigenvalue or characteristic value omega n, and omega n actually, as we know, omega n is equal to pi c divided by L. And the set omega 1, omega 2, etc. okay, is called the spectrum of the vibrating string. Alright, so the vibrating string has fundamental frequency when n equal to 1. So the fundamental frequency is the pi c over L. And for the others, they are harmonics. Okay, you know every string has a frequency, right? Corresponding to scales. So, for example, the C, D, E, F, G, and B, right? C, D, E, F, G. So that they repeated, okay, by the Bach, right? Bach, I forgot. Maybe it's 14th century musician, I think so, 14th or something. I forgot it many years ago, right? So that he actually created a theory about the scales, and so they are frequencies. So every in instrumental music, every string has the fundamental frequency. Okay, so omega 1 is the fundamental frequency. And omega 2 over 0, as you can see, they are multiple, right, of the fundamental frequencies. So they are harmonics of the fundamental frequencies. And the quality of a string depends on the component of the weighting in each harmonics. Okay, even though you have two strings, they have the same fundamental frequencies. But the quality of the sound created by these two different strings will different when you hear them. And that because this is because the component in each harmonics are different. Okay, so it's different. Now, so that you can see that this is the so they call the spectrum there. Okay, and so now, so we know that each eigenfunction U1 xt satisfy the two boundary conditions in 12.3.6. Oh, by the way, the boundary conditions in 12.3.1. What? I already erased it. Since the U1 0t is 0 and U1, okay. So this is the F and 0 and the G and T. And this is 0 and U and LT. It's F and L, G and T, which is 0 for all t greater than 0. Okay. So each eigenvalue, by our construction, that they satisfy the two boundary conditions in 12.3.1. But they may not satisfy the initial conditions. Okay? So they are. So now, so this is the problem we have to solve. Okay. So step 3, we want to in this we want to know solution of the migrating problem. All right. So now we have still at the end of step number 2, we are successful to find solutions which satisfy the one-dimensional wave equation as well as the two boundary conditions. But we don't know whether that the solution or eigenfunction satisfy the two initial conditions or not. In general, this is not true. Okay, as you can see by checking. Now, okay, so what can we do? Now we won't use the superposition. Okay, so since the wave equation is homogeneous and linear. Okay. Okay. Any superposition of eigenfunctions so we say U of xt, okay, and the Bn sine omega nt plus Cn sine omega nt and the sine n pi Lx. Right? So this the superposition is a solution. Okay, it's a solution of the one-dimensional warp equation. Okay, in 12.3.3. Okay, this is by theorem 12.1.1. If the series converges, right? So if the series converges, then that of course it satisfies the our one-dimensional equation. Okay, and because our boundary condition is homogeneous, okay, so it can be seen that uxt in a graph, okay, also satisfy the boundary conditions. Okay, in 2.3.1. Okay, the boundary conditions there. Okay, and so now we're imposing the initial conditions in 12.3.2 on the uxt. So we have here, we have that the u of x0, okay, which is Bn, and the sine n pi Lx is equal to f of x for all x in 0L. Okay. So this is the initial diffraction. Okay, and the initial diffraction equal to f of x. Okay. And also the initial velocity, okay, u sub t of x0, again, when we have, so if we take the derivative, right, the partial derivative with respect to t, so we get, right, and then this is minus b n omega n, and the sine omega n t plus Cn omega n cosine omega n t. All right, so this is the derivative. And we should use what we learned in chapter 11, right? We have some theorems to guarantee that we can do the derivative, on the expansion directly. Okay, on the expansion directly, according to some properties, right? But now we just say all of these properties are satisfied. Okay, so we just do it, and so when when we put the 0 there, this is 0, so this is 0, and we have that one. Okay, and this is equal to Cn omega n, and the sine, alright, n pi divided by Lx. Oh, this is sine n pi Lx. I forgot to put them. Okay, so this is 1, this is 0, so you get there. And this is equal to g of x for all x in 0. And you can see, what is that? This is just the so-called the half-range representation, right? Of f of x. We discussed in section 11.2, right? The half, because f of x is a function in Z and L. So we regard f of x as the one half of an odd function, right? Odd periodic function with period 2L, okay? With period 2L. And so we have a sign only, right? Because this is odd function. And similarly, g of x can be regarded as, well, as the one half of a periodic function with period 2L, okay? And so that we have the Fourier sine series representation there. Alright, so now we must choose Bn and Cn. Okay, so that u of x0 and ut of x0 are Fourier sine series expansion of f of x and g of x on 0 respectively. Okay, and so from section 11.2, so we have that the Bn is equal to 2 divided by L, 0 to L, f of x, and sine n pi divided by L, x dx. And the coefficients, and omega n, Cn equal to 2 divided by L, 0 to L, g of x, and the sine n pi divided by L, x dx here. Okay, so this is what we have that. So by regarding f of x and g of x as being half the range of two odd periodic function with a period 2L, okay, respectively. know that, as we have shown, that we know that F0 is equal to F of L is equal to 0, and G0 is equal to GL is equal to 0. Right? We already make a remark before, so that we have, and so that so this is quite nice. Right, and so we will assume that both f of x and g of x have piecewise continuous derivative. It's a piecewise continuous derivative. Okay. All right. So that's a formal solution, right, of the vibrating problem is here. So u of xt, so we find okay, a solution ready, and so is that is cosine omega nt times 2l f of x sine n pi divided by l x dx here, okay, plus sine omega nt to omega n divided by l g of x sine n pi x and dx together, and the sine n pi lx. Alright, so we have formal solution, and just like we studied in section 11.3, right? And there we created a solution, a conjectural solution, alright, of a series of sinusoidal functions. Yeah. So we have to check whether they are indeed solutions, right? And so the formal solution. So this here we have for 12.3.7. Okay. So the formal solution in 12.3.7, okay, becomes a true solution, provided that the series in 12.3.7 converges, and the soul due the series obtained, okay, by differentiating it twice termized with respect to x and the t, and I have the sums equal to U respectively. And which satisfy the verb equation. Okay. Okay. So we have to check a lot of things. Okay. With our knowledges learned in chapter 11. Okay. Any questions? Okay, and so there are some okay, so there is further discussion on the solution in above. And the supplemental lecture notes. Okay. All right. So I will distribute it to you. Okay, by tomorrow. Okay. I almost finished it. Okay. So I stop here. Any questions before we leave the classroom? Okay, good. So I stop here.